So now we have seen how to do our classification as a binary classifier. So it was a binary classification problem. So we had different points for one class and we had another class. So it was basically 1 or 0. It was basically a binary classification because we had two classes. Okay. So what will happen if we have multiple classes and we need a classifier to classify all of them? Some classifiers has like a built-in capability of handling multiple classifiers. In the meantime, we could use multiple binary classifiers to achieve what we want to do here. How? We could, let's say that we have 3 classes and we need to classify our sample. We could basically say that this is the positive class. We would have a classifier that will consider this as a positive class, and it would consider C2 and C3 to be negative. So it will be a binary classifier just considering this to be the positive class, okay? And we could have another classifier. So now we had one classifier, okay? Classifier that considered C1 as the positive class. We could have another classifier that considers C2 as positive and C1 and C3 as negative. And a third classifier that considers C3 as positive and C1 and C2 as negative. Okay. We say that this procedure of building multiple classifiers like that, we say that this is one versus rest. Okay, that's one versus rest classification. Why are we saying this? Because we are taking one of them versus the rest of the classifiers. The rest of the classes, sorry. One versus the rest of the classes. Okay. So we have an idea on how to do one versus rest. So how about the labels? How about the labels? So let's say that C1 had the label, the true label 1, and C2, 2, and C3, 3. Okay. I think now this will be an issue because when we had our sum squared error, we were taking y hat minus y. We were looking at the numerical difference between the predicted value and the true value, right? But here there is an issue. Why? Because if we use our labels like that, the difference between class 1, which has the value of 1, and the class 2, which has the value of 2, that's only 1. The difference is 1. And this is not the same as the difference between class 1 and the class 3. The difference is 2. Okay, so that's now unfair, right? We need to have multiple values with equal distances. Okay, because we could take this predicted minus the true label. The distances between the classes should be the same because all of them are different. All of them are unique. Okay, so the distance between them should be the same. So people thought about having a new method in which we could encode the value of every class in this manner. We call this one hot encoding. Okay, one hot encoding means that if you have your 3 classes and you know that the value of the first sample, the true label of the first sample that you have is C1, basically you can encode this value with the number of classes. So instead of having one value representing y, and it could just take different values, and instead of having one value for y, we would have a value that equals the number of classes that we have. So instead of having one value for y, we would have 3 values, one for C1 and C2, and one for C2 and one for C3. So if the true label we know that the true label for this sample is C1. We will put 1 here, and we'll put 0 and 0 there. And if the true label of the second sample is C2, we'll put 1 here and 0 there, and so on. Okay, if the new one was also C2, if it was C3, it will be like that. Okay, so any questions on this part?
No.
Okay, good. So right now we had this one hot encoding solving this issue for us. Okay, now we need to know how to do our classification. We can do our classification in this procedure, one versus rest, because now you can just look at this, right? You can just look at this. You would see that this is one when the sample was for C1, and when it was for C2 or C3, the value will be 0, right? The value will be 0. So basically, I can train my first binary classifier on C1 like so, because it will see this as the positive class and it will see anything else as the negative class. So this would be the labels of my first binary classifier that we talked about. Okay, and this will be the labels of my second binary classifier, and these are the labels for the third one. Okay, if you are trying to visualize this, and let's consider that we have our classes to be RGB. So let's say that C1 was R, and then we have green and blue. Okay, so let's say that these were our classes, and we need to classify them. We need to classify them. So we have red, green, and blue. Okay, so right now you wouldn't have one decision boundary, because let's think about it. We have now not two classes, we have three classes. So we wouldn't have one decision boundary. So let's think about that. When we consider the red class to be positive and anything else to be negative, red class will be positive and everything else will be negative. That's a binary classifier, right? Considering this positive and everything else to be the other class. This will give us a boundary, a decision boundary that will look like this, because it will just classify the positive and negative and try to discriminate them like so. So the negative in one side and the positive in one side. So how about the green? The green classifier will be classifying this against those. So it will draw something like that. Okay, because it separates the positive from everything else. But what the blue classifier, it will be drawing a boundary like that, because it's separating positive from negative. Okay, now let's consider this problem. Now we would have different classifiers, each one of them giving us a result. Okay, the final output, if we are using something like logistic regression, we can look at the one that will give the highest score, because the true label of this is 1. If our predicted value is like 0.8 here and 0.1 in this classifier and 0.1 for this classifier, then we would say that our unseen sample should be red because it's very close to this one. Okay, so we basically take the maximum of the three output values of the three classifiers. Okay, so this is actually nice because it could show us that there is a problem with such classifiers. Do you see this region? This region doesn't belong to any of the classifiers. We say that this is an ambiguous region because we don't really know what is happening inside of this region. Okay. So it was just nice to visualize this because now with this multi-classification, it is not perfect because if something falls and something that we cannot decide on, that could be assigned something randomly, or we could use another classifier that has this multi-class classification like built in inside the mathematical formulation of the classifier itself. Okay. And by the way, this is with our classifiers, of course, it will be very unlikely because all what we are coding here or what we are describing here is just one classifier. And in a neural network, we would have multiple classifiers. So this issue wouldn't even be an issue. Okay. So any questions in this part?
No.
Okay, good. So let's consider what will happen when we take the values from these different classifiers. So I will just put this again. So it was looking like that, and that's our true labels. So how about the predicted labels? Okay, so we had our W transpose always multiplied by X to get Z, and then we go apply 5Z, which is a linearity. So it could be an activation function like a sigmoid activation. And then we say that this is our predicted value. This predicted value could range from 0 to 1 if this is sigmoid, but if this is linear, it will range from minus infinity to infinity, right? If this is a different activation function, okay, it could range from 0 to infinity, or it could range from minus infinity to infinity again. So it really depends on the activation function that we're using. Okay, so our predicted labels, our predictions could be continuous. Our predictions could look something like this. Just a bunch of continuous variables. Okay. So now we have a problem. Why? Because if we had positive values, if it was like 90, 10, and then 10, not minus 10, we could say that, okay, fine, let's transform this into a probability. Because when it was sigmoid, we said it's 0.8, 0.1, 0.1. This would sum to 1. If we add them together, this would sum to 1. Okay? But the issue that this is continuous. Okay? So it doesn't sum to 1. Okay? So if they were positive, we would just say, okay, fine, let's divide each one of them, like 90, by the total, by the summation. If you do this for positive numbers, this will transform this 90 into a probability. Okay. And you do the same, of course, for the other one, divided by the same summation. And this one as well. Okay. This will give us the probability, correct? But the issue comes when we have negative numbers, because when you add negative number, then this would actually decrease like the summation of them. Okay. So right now we need something that will transform this negative number into a positive number while having the same scaling, while knowing that this negative 10 is still very far from 10. Okay. So how would we do this? We can use the exponential. We can use the exponential of the value that we had common from our 5z. So let's say it was a linear like this. So z will equal 5z. Okay, so we would use the exponential of z. Why would we do this? Because let's think about it. Z could be from minus infinity to infinity. Okay, then what would happen to the value of the exponential? The exponential would range, so that's the value of z, but the value of the exponential would be different. The value of the exponential itself, when z is minus infinity, the value would be 0. And when z is infinity, the value will be infinity. Okay, so this is really nice because the exponential has now converted our data from being from minus infinity to infinity, so it could have negative numbers. Now it doesn't have negative numbers. Now it's ranging from 0 to infinity, so we wouldn't have negative numbers. Okay, and that's something with the power, because 2 of the power of negative 10, that wouldn't be negative, right? Okay, but we use the exponential because that's a very famous function, and it will give us a clearer value. Okay, so by doing this, we have transformed our data from being negative or being looking like this into being all positive. So right now, every value will be e to the power of the only value. So the first step will be like this. So 90 will be e to the power of 90 over e to the power of 90 plus e to the power of 10 plus e to the power of minus 10. The second one will be e to the power of 10 divided by the same thing. Okay, so I will call this summation. So I will just put summation here because it's the same thing. Here e to the power minus 10 divided by the same summation. Okay, so any problems with this? Any questions? So here we had e to the power e equals 1, and it goes on all classes. And this is the summation of all e of z. So we can say that this is the general equation for this. We take e to the power of z divided by the summation across classes of e to the power of z. Okay? And this is actually called the softmax. And here we have known how to convert our continuous value of the prediction into a probability using softmax. And of course, the summation of this, if we add this to this to this, they will sum to 1. So we have successfully converted our output values into probabilities. Okay. And then we can take the maximum. So if we looked at the probabilities and we find that this is 0.8 and this is 0.1 and this is 0.1, so they sum to 1, okay, and this is the maximum value, then we take this to be our true class. We say that our sample is belonging to class 1, okay? So we take the highest probability because, again, the probability of such algorithms in general would reflect something else. They are reflecting the distance from the boundary. So we could say that a sample falling very close to the boundary is not very high in terms of its probability, and a sample very far from the boundary and belonging to the X class, it has higher probability. We could call this the confidence. We could call this certainty. We could call this posterior probability. Okay. So basically take the maximum of that to be our class. Okay, so any questions at this part? Any questions? Okay, so now we can go to the code of doing this multi-class classification. Can you hear me?
Yes.
So we can go to the code of doing this, and let's go on this code step by step. Can you see the code clearly, or should I zoom in?
It's clear.
Okay. Okay, so in this example, we will be using a data set that is real. So we will be using MNIST dataset. So these are handwritten digits from 0 to 9. Okay, and they were images. So basically, we have two dimensions. We have height and width, and we'll be trying to go through this code step by step and see how we can do our multi-class classification of these digits. Okay, so basically in the beginning, I'm just reading the data. And here I was changing the dimensions of my data, because if we look at this, you would see that we have 28 by 28. That was the height and width of every image. And we have a lot of training samples. So I just wanted to put samples in the first dimension. And that's what I am doing with this permute function. It's just changing the order of these dimensions. Okay, so now I have put my samples in the beginning. I'm here reshaping, meaning that instead of having my image 28 by 28, I'm reshaping my data according to the size of the first dimension, and I'm not keeping the second dimension. I'm putting the second dimension as any, meaning that I will keep the first dimension, okay, and the second dimension and the third dimension will be just one dimension. I'm just reshaping the 28 by 28, and instead of having this as a matrix, I will have it as a vector. So after running this, you would see that now they are one dimension, okay? And then I'm putting the labels. Now the labels are of course from 0 to 9, because from 0 to 9 are the digits, okay? The handwritten digits. So we have 10 classes, okay? And here I was just reducing the dimension of my data, because with the images we have some values. Um, we have some values at the end of the image that do not have any value basically. So if we can imagine that we have our samples looking like this, every sample is an image, and the image has a digit written inside of it. So the edges of that image, the edges of that image could be empty, could be empty. If even if you like drew any character inside of here, any digit inside of here, it could be empty, the edge pixels. So that's why here I was just reducing my features by ignoring the edge pixels. Okay, you may do this or may not, it's fine. Okay, and I'm just transposing the data. And these two lines, feel free to go ahead and see what I'm doing here, but I'm basically doing one hot encoding. And instead of doing this in a loop, I'm calling built-in functions that will handle this one hot encoding. And I really encourage you to try to think about your code in this way by calling in built-in functions and trying to make this easier for you instead of doing for loops. Okay, so basically this will convert our y from being from 0 to 9 into being one hot encoded value. Because we have 10 classes, because we have 10 classes, if you if you remember, we said that we would have our y, it will be extended into C1, C2, C3, and this problem. Okay, but now we have 10 classes, so our y will be extended into 10 different columns, okay? And each column will have a number of rows equal to the number of samples. So we'd have dimensions of number of samples and number of classes. In our case, it will be 10. If you look at this, yes, we had this, because if you look at this, we have the number of samples and the columns are the number of classes. Okay, so any questions in this part?
No.
Okay. So here I'm fixing uh, this random generator seed such that the result will become reproducible, meaning that I can reproduce the result if I just shut down the machine and open it again. It will be producing the same random number. Okay. Okay. Uh, Here I'm initializing my weights and bias, and I am putting the weights and bias together. Okay. And that's just a detail because we can imagine we can imagine that if we have our weights, because we were multiplying the weights with the x value, but we were not multiplying the bias. So we could imagine that we can assume that the weight that we will put here is a bias. We can assume that we have the bias as a weight, okay, that will be multiplied not by x, but will be multiplied by ones, such that when we do this multiplication, you will just use this multiplied by this. So it will be W transpose X. It will be multiplied by the values of X, and B would be multiplied by 1. So it will be plus B. Is this clear?
Yeah.
Okay, good. So by doing this, we will be just aggregating the value of the bias and doing the calculation of our net input at the same step. Okay, so here I have initialized my weights in a different way. So because here we have a lot of classifiers. So how many binary classifiers would we have in the code? What do you think? What would be the number of binary classifiers?
Two.
Can you say this again? I didn't hear.
Two.
No. So how many classifiers did we use when we had 3 classes? We used a classifier for each one, right? Each one considered its class to be positive and others to be negative, correct?
Yeah.
So we used the 3 binary classifiers. So now we have handwritten digits going from 0 to 9. So we have 10 classes. So we would have 10 binary classifiers. Okay, so is it clear why we have 10 binary classifiers or?
It's clear.
Yeah, okay. So we'd have 10 binary classifiers. So each classifier is optimizing a weight. Each classifier trying to get Z, okay, and optimize the weights. So we'd have 10 of those classifiers. So what I try to do instead of calling this W1 and just have a lot of weights and this the classifier of the weights W2, W3 and have a lot of weights, I try to aggregate all of them into a matrix of weights. So basically I would have my weights looking like this. I would have the number of classifiers, which is 10, by the number of features. Because every weight has the same number of features, has the same number of features as the X value. So every weight is just a vector that will be multiplied by the data X. Okay. So with every time, with every classifier training, I would just take the value of the corresponding weights of that classifier. So for the first classifier, I will take this and then multiply it with X. Second classifier, I will take the second row multiplied by X. Is this clear?
Yeah.
Okay, good. So right now we can see the code that it's achieving exactly that. So I have initialized my weights like so. So it has two dimensions. Here in the explanation, I showed you the number of classifiers by the number of features, okay? Here in the code, I'm just transposing this. It was the transpose of this. So it has the number of features and then number of classifiers. So we have like 700 features and then 10 classifiers, okay? And then the bias will be 10 values, one bias for every classifier, because again, the bias does not depend on the features. It is just one value. So it will be one value for every classifier. That's why it has 10 values. Okay. And then I'm putting the ones underneath the X values, the thing that I was describing here, that we are putting ones underneath X values to get the bias directly, okay, when multiplying the weights. And then here I'm also putting the bias at the end, which is similar to this, okay, putting the bias at the end. Okay, here we are specifying our parameters, which is something that we have done several times, like the epochs, how many iterations. And here you will find that I was putting batch size. You can completely ignore this because I didn't want to take the whole training set at once. So I was just splitting this into different batches. That you don't have to do this, okay? So you could assume that I'm not including this, and I'm not also including this for loop on the batches. Okay, it's totally fine. If you would like to see the implementation of the mini batch, that's good as well. Okay, so we will be looping on epochs, and we will have a loop on the classes because now we are constructing 10 binary classifiers, as we said. Okay, 10 binary classifiers. Okay, each one of them will have different epochs, will have different iterations, and we'll be optimizing inside of each one of them. So here I'm looping on the classes, I'm looping on the 10 classes. Okay. Okay. So here I'm taking the labels. So basically from this matrix of one hot encoded values, I'm taking just the first column. Okay. Why am I taking the first column? I'm taking this of class. Class is one. You can ignore this part because that was the mini batch, okay? And this is one. So that's basically our iterator one. So it will take all rows and the first column, which is exactly the one hot encoded value, all rows and first column, one hot encoded value for class one. Okay, one hot encoded value for class one. So basically it means that this class is the positive and anything else is negative. Okay. And these will be our labels. And then we go ahead and get the weight that we want. So basically we would be getting all the rows and the first column, again, the weights associated with the first classifier, okay? And then we will be multiplying those with X. So this is similar to what we were saying here, that we will be getting this and then multiplying this with X. I'm just here transposing this because I was transposing the W matrix because in the code I initialized this as features, okay, by classifiers. Okay, that's why you would see that I'm using all and then class because I'm taking all and then class. I'm taking the vector like that, okay? And then I'm transposing this to make it a row vector and then multiplying this with X. And you would see that's indeed what I'm doing. I'm taking the transpose and then multiplying this by X. So any questions?
No.
Okay, so this will give us the value of Z, the net input. Okay, and then we can apply our sigmoid function. Okay, and that's our sigmoid function, and that's our phi Z or the predicted value. And then we can calculate our um, cost using the cross entropy cost. like before, okay, and get the value for the error. And then we can update our weight by just taking the weight minus eta, and then, of course, the predicted minus true multiplied by x value, and then we divide by the length, okay? Like we did with the sigmoid, uh, I'm sorry, with logistic regression, okay? And this would be our weight. But let's remember that we are still with the first classifier. We are inside the first classifier. So that's why you would see that I'm not accessing just W, I'm accessing this particular column of W. Okay, the first column, because our weights are now in a matrix. So I'm just here accessing the first column of that classifier that I'm optimizing. And then I will be going to the second column, the third column, and so on, and will be looping over epochs as well. Okay, so that would be the first weight, put it in the respective position, and then loop again for the second, and third one, and so on until we finish the number of classes, the number of classifiers, and we also finish the number of epochs. So any questions in this part?
No.
Okay, so here we have just a breaking condition that we can break from our loop if we have a value for the error, okay, that is lower than 0. If the value of the cost is basically 0 or very close to 0, we could break if we make this like 10 to the power of minus 10 or something. If our cost is lower than that, we can break instead of going through all the epochs that we have. Okay, so right now we have 10 classes trying to optimize, and each one of them, now we have a true data set, we have a real data set, we have a lot of training samples. So it will take time. So here I just let it run and it will take a little bit of time. And here we have a figure in which I'm trying to plot the error, okay, and epochs as well. So we would see if with increasing the number of epochs, if we would have less error. In logistic regression, we just had one curve because we had one classifier. In this one, we would have 10 curves. So I was color encoding those. You would see 10 curves, and each one of them is trying, or each one of them will decrease with the increase of number of epochs. Okay. So let's just wait and see the output of that. Okay, so it finished. So you can see this figure right here. So you can see that I have taken a label, I have color coded each one of them. So 0 to 9, these were our classes, okay? And 0 is blue. So you can see that the blue curve is starting when we had the first epoch, it was giving high error. And when we increase the number of epochs, when we iterate over our data, our whole data set, the error is getting um, lower, okay, which is really good. So we can even look at one of these curves and try to interpret it. Like, see this curve, and this is the orange curve. The orange curve here is 8, okay? So the character 8, okay, or the digit 8 and the digit 9, which is yellow, both of them had an error and it was almost the same, and they are very close to each other. So most likely our classifier was confusing 8 and 9 together, and it wasn't able to see the value for 8 and 9 very clearly. And also you can see the value for 6. So it was confusing 6 and 8 and 9. And you can see 6 and 8 and 9 because 6 is this color right here, and it's also almost constant. So when we are increasing the number of epochs, we didn't gain much because it was very difficult to differentiate between 6 and 8 and 9. But this is really very nice because that's intuitive, because the written digit of 6 and 8 and 9, they look a little bit close to each other, okay? And that's why our classifier was confusing them, okay? So it's very nice to see such insight from these curves, just to look at the performance of our classifiers with the increasing number of epochs, and just see the error for the classification of each one of those classifiers, because each one of them is trying to handle a specific class, a specific digit. Okay, so do you have any questions in this part?
No.
Okay. Okay, so here I tried to test my classifier, okay, but here I didn't do cross-validation. So of course, in a real problem, we would be having a cross validation, okay, if we are trying to optimize a parameter or something. But here I didn't do cross-validation on my training set, okay. I just have a specific training set. So I didn't want to optimize any parameter, so I was just training with my whole data set. The nice thing is that here in this MNIST dataset, we have a different dataset just for testing. So we can use this testing set. So I loaded the testing set, okay, which has fewer number of samples. And here I was doing the same manipulation of data. I was reshaping the data so that the images will become vectors, and appending them with ones for the bias. So I was basically doing the same thing I did with the training set. And then, because we have 10 classifiers, we will be obtaining a label for each one of them, labels for each one of them. We will be looping on the classifiers and then projecting our weights, okay, on the testing set. We will be multiplying the weights of every classifier with the testing set. We will get our Z value, and then we'll use the sigmoid to get our 5Z, okay? And we will store this into this matrix of 5Z. So that's the 5Z of the first class. And if we loop, this would be the 5Z of the second class. You would see that the columns are now 2, and so on. So when we finish this, we would have the number of samples by the number of classes that we have. Okay. And this is right now is 5Z. Okay. So this is exactly describing what we were explaining here, that we will have a matrix y hat, okay, of y hat. It will have number of columns equal to the number of classes. So yes, the number of columns here are 10, okay, and we'll have number of rows equal to the number of samples, and we have here number of rows equal to the number of samples, okay. Right now we need to do something that we introduced in this slide. We need to do softmax, right? Because now these values could be continuous, okay? If we're using a linear function, here we were using sigmoid, but we could use a different function, right? So we need to convert them using softmax. So by doing softmax, we will be using the exponential of the value divided by the summation across different classes. And if you look at this line, I took 5z, okay, which is um, the predicted value. And then I took exp, which is exponential to the power of that value. So it's e to the power of 5z, e to the power of 5z. Okay. Here I put z because we were using a linear function. So z equals to 5z. Okay. And this will give us s value. And then we will divide by the summation across different classes. And here at this line, I was dividing by the summation for different classes. you could trace this part. Here I was just repeating the matrix with the summation because I find this easier than doing a loop or something like this. Like instead of looping on each one of them and dividing each one by the summation, here I was just repeating the summation with a with the same number of columns and just dividing them at once. Okay. So anyway, you could implement this differently in Python. It's up to you. But anyway, e to the power of z and then divided by the summation, and this will achieve that. And then we can safely now take the maximum of these values. As we said, we will just take the maximum across the second dimension, across the columns. So what will be the column that will give me the highest probability? That's why I'm taking the maximum of S across the second dimension, the column. Okay. And here you can find, I named this posterior for posterior probability. And you would find that this would be the maximum value here, and this would be the maximum value there, and so on. And if you check S, this S value should be gathering all the probabilities. So if we sum this, actually we can do this in the code right now. If we sum this across columns, it should sum to 1. So let's test this. So if we take S, let's say that we have a variable called test sum, okay, and we are adding S across the second dimension. So we're basically taking this, adding all of this together. So all of these should be sum to 1, okay? Okay, let's check the value of our new variable test sum, and then you would see that all of them are adding to 1, exactly 1, okay? So any questions on this?
No.
Okay, perfect. And then what I am doing here, I took the value of the prediction because the value of the prediction here is getting the index of the maximum. Okay, so here I went to the index of the maximum. So the index of the maximum, because if you look at this in the slides, you would see that here I was taking the maximum, it's 0.8, but I don't really want to take the value of the maximum itself when comparing to the true label. Of course, it's very relevant because it's the probability. But I want the index of that, like 0 or 1 or 2, because that's the class, right? That's the class label. So here I was taking the prediction, okay, because the prediction will give me values from 1 to 10, but the digits, the true label, are from 0 to 9. I was subtracting 1. I was subtracting 1, okay? And I was also doing a manipulation for the labels here, okay, to encode them from 1 to 10 and instead of from 0 to 10, okay? Because with this, I will be able to apply one-hot encoding. Otherwise, I wouldn't be. So I applied this trick here. I added one, and here I subtracted that one to then be able to compare them. Okay. Feel free to ignore this if you are using Python and trying to do one-hot encoding in a different way. It's totally up to you. I'm just explaining what I did with the code. Okay, so right now I've just subtracted the 1. So we have our labels from 0 to 9. And then we can compare the predicted label with the true label. And we can multiply this by 100 to get our accuracy. The accuracy that we have is not very high. We just have almost 50%. Okay, so it is not very high accuracy, but this actually will point us to um, the thing that I would like to talk about right now, which is the chance level. Okay, if we are flipping a coin, okay, there is one chance for head and one chance for tail. Okay, so we say that the chance is 50, 50, 50. Okay, it's 50, 50. So basically, if we have a binary classification problem, The classifier has two options, the positive class or the negative class. Okay. So if our classifier was completely random, just picking the class randomly, it would classify at 50%. Okay. Because it's either positive or negative. It doesn't have any other options. Okay. So we say that the chance level in binary classification is 50%. This would be the accuracy that you get by chance if your classifier was completely random, not learning anything, because it just has two options. Okay, so how about the current classification problem? We have from 0 to 9, so we have 10 options, right? We have 10 classes, true? Then our value wouldn't be 50%. Our classifier wouldn't be of 50% chance. If our binary classifier was classifying 50%, we would say this is a very bad classifier because it's not learning anything. Okay, it's just picking the classes randomly. But for our multi-class classification, we have 10 classes. So the probability of each one of them is 1 over 10 because the probability of each one of the classes in the binary classification was 1 over 2, the 0.5. Okay, that's why it was 50%. But here it's 1 over 10, okay, for our 10 classes, okay, which is 0.1 multiplied by 100, it's 10, okay? So we have 10% chance level. Okay, so now the chance level of our classification is 10%. So to get a classifier performing at 50% that we had, or exactly 47% that we had in our code, this would mean that the classifier is not very bad eventually. Okay, because it's far away from 10% and it had a lot of options. So it could have had made a lot of mistakes in the way, but it doesn't. Okay. Of course, it's still not a very good classifier. Okay. But still, that's an intuition behind the chance levels. And if you had 20 classes, you would have 1 over 20. Okay. Chance level. So the classification would be even harder. Okay, so do you have any questions on this?
Mm,
Okay, so
No.
the last thing I would mention in today's lecture would be what we were doing so far can be summarized as one node. We call this node. A node is a classifier. So we could say that all we were doing, like a logistic regression, is actually one node. And we could say that inside of this node, we are getting Z, okay, and we are getting 5Z. So we can say that this is one node. All of this is one node, okay? And the output, the 5Z output, we can call it A for activation, okay? We can feed this to another node, to another classifier, okay? And we can even construct several nodes like that. The first, the first part, we call it layer. So this is our first layer of nodes, okay? And this is our second layer of nodes, okay? And when we are feeding the output of this to all of the other classifiers of the second layer, we say that this is a fully connected classification, okay? If we have multiple nodes like this, we call this a neural network, a neural network, okay? And when we are just feeding each of the classifiers from the second layer with all of the classifiers of the first layer, we're connecting the nodes like this, it's fully connected. And it's coming from the name, it's fully connected. All of them are connected to each other. And we can also call it dense. Okay. So when we say we have a dense layer, this means that it's fully connected. Okay. So if we have our features, if we have our features like that, we could basically say or name this as the input layer, and this is fed to this feature fed to every classifier, of course, because every classifier will see all the features, okay? And we can call all the layers in here hidden layers, okay? Because they are hidden in the middle between the input layer and the output layer. So this will have the final prediction, okay? And this is our output layer, okay? So you would have a classifier giving its value to another classifier. So you are feeding X values with some weights to calculate the prediction here, and then feeding this as a feature. So this classifier is treating the previous node as a feature, okay? The previous activation as a feature, okay? To get its value, and then it gets its own value to the output, okay? So we are feeding forward, okay? And when we are calculating the weight updates, we have to look at the true label. We only have the true label at the end, okay? At the end, we can only get y hat at the end. So when we get y hat at the end, we compare it with y, and then we see our error, and then we back propagate our weight. So let's say that we have a softmax, we get our error, and we know the error that we are doing, we need to back propagate our weight. So we are getting the error here. So we are updating the weights associated with that classifier, and then going and updating the weights of that classifier, and then updating the weights with X. Okay. That's why we call this feed forward back propagation neural network. So we call this feed forward back propagation neural network. And it makes sense. We called this each one of them a node, a neuron, okay? And this is forming a network. That's why it's called a neural network. Okay, a lot of terms here, but it's very important to think about them. Okay, and also if we have more than one hidden layer, like in this example, we have this layer and we have this layer. If we have more than one hidden layer, we say that this is a deep learning model. So actually what we have here is a deep learning model or a deep learning neural network. Okay. So that's like the core of machine learning or deep learning is coming from those nodes that we have tried to explain them in the previous lectures. Of course, you can plug in any different activation, you can use different optimizers. You are free to do whatever you would like to do. Okay. Right now we have one thing left, okay, to understanding this whole neural network, okay, and other deep learning models is how to update the weights, how to update those weights, how to back propagate the weight, because we looked at delta W, okay, but delta W is basically this part, right? Just comparing and then going back, correct? Then how would we back propagate the weight all the way and update the weights of different classifiers of different layers? This will be something that we will cover next time, okay? And we will talk about different other classifiers like decision trees and other classifiers as well. Okay, so do you have any questions? By
No.
the way, they call this a neural network or artificial neural network. Just please try to memorize those terms and try to just stop at this slide and try to um, really memorize those terms because we will be using them next time.
Honestly.
Okay.
Okay, okay.
Okay. Thank you so much, Muhammad, and we will have a lecture next
Frank,
week, and let's keep in touch via email. Okay.
next week will it be like Monday or Tuesday?
So let's talk about this on email. Okay.
Okay, okay.
Okay, because
Thank
the
you.
time could be different.
All right.
Okay. Thank you and take care.
Thank you so much.
Thank you.
Online? Mm-mm, not offline.